Hello everyone, my name is Robert Gifford. I'm from the University of Pennsylvania, and today I'm presenting DNA, Dynamic Resource Allocation for Soft Real-Time Multicore Systems. This is joint work done with Neeraj Gandhi, Linh, Phan, and Andreas Haeberlen. Modern day systems continue to gravitate towards multi-core platforms. While this is generally a positive trend as it provides more computing power for a smaller energy footprint, there are also some downsides. Tasks running on multiple cores can now access shared resources simultaneously, leading to contention and interference. For example, if you were to run a benchmarking application on core 1, while also running interfering tasks on cores 2, 3, and 4 that heavily use cache and memory bandwidth, we would expect the task on core 1 to run more slowly. Looking at the graph on the right, we can see just that. The first two bars represent the Keneal application from the Parsec benchmarking suite. We can see from the red bar that when Keneal runs in the presence of interfering tasks, it runs 40% slower than if it were to run in a fully isolated environment. Ultimately, resource contention can lead to deadline misses which are unacceptable in a real-time system. One approach to mitigate such interference is through static resource partitioning. We can use techniques like memguard to partition memory bandwidth and Intel's CAT or cache allocation technology to control the last level cache so that each core is better isolated from one another. Using memguard and CAT, we can ensure that execution times are consistent by statically allocating each core their own independent resources, thereby preventing interference. However, the efficiency of this approach is less than ideal. To see why, we must first understand how a task's resource needs can change over time. In the graph above, we show the FFT application from the Splash 2x benchmarking suite. The blue line represents the task's overall rate of execution, while the yellow and red lines represent the number of cache requests and cache misses respectively. These lines are plotted against the number of instructions the task has finished up to that point, which we refer to as the number of retired instructions. If we were to provide a low amount of resources, say 2 cache partitions and 2 memory bandwidth partitions, then we can see that the task's rate of execution follows 3 phases, going from high to low to medium. These phases are going to be unique per application. Comparing against Keneal from Parsec, we can see that there are also 3 phases, but the transition between them is far more gradual and the duration is dramatically different. These phases are also unique within a given application, depending on the number of resources that we provide. Giving FFT and Keneal 18 cache and memory bandwidth partitions, then we can see that the phases are dramatically different. Now, one might expect that providing more resources would always lead to an increase in a task's rate of execution. But with FFT, we can actually see that this is not the case. For the first phase, which lasts for roughly 1/3 of the task's overall execution, we see that providing more resources yields an almost identical rate of execution. Therefore, if this was a static resource allocation scheme, then providing 18 cache and memory bandwidth partitions would be wasteful due to the fact that 1/3 of the task's lifetime doesn't benefit from additional resources. Based on this insight, we present a novel phase-aware resource allocation technique that can achieve both good isolation and good resource efficiency. Our approach provides a way to characterize a task's resource needs into different phases and then leverages these to dynamically adapt a task's allocation at runtime. This idea culminates into two novel resource allocation algorithms. The first, DNA, utilizes phases to allocate resources to tasks to maximize rate of execution, while the second, DADNA, further takes into account the task's deadlines in order to maximize schedulability. Next, we will discuss how we define and identify phases, and then cover the DNA and DADNA algorithms in more detail. To understand how DNA and DADNA effectively allocate resources, we must first properly define what a phase is, as well as figure out how to track what phase a task is currently in. As we saw from the Keneal and FFT rate graph shown earlier, it is clear that a task's phase is tied to its overall progression. Therefore, it is important that we keep track of this information. To do this, one may try using the wall clock time. However, this won't end up working because it can vary heavily from one run to another, depending on when the task is scheduled. Another idea is to use the task's instruction pointer, although this doesn't work either because it can repeat itself due to branching logic like loops. We need a value that is guaranteed to increment in one direction while being consistent from run to run. Our approach is to use the number of retired instructions. We make the assumption that a task is deterministic given the same input, and so it always needs to execute the same number of instructions to finish. We found this metric performed very well when given periodic tasks with similar inputs, which are a typical workload for real-time systems. Ultimately, DNA and DADNA are not dependent on the specific way of tracking phases, and we could always use other metrics for more complex tasks. We now have a way to track the progress of a task and therefore what phase it is in at any given time, but we still have no information about the phase itself. To gather this information, we profile each task offline in a carefully controlled environment. For each profile, we collect the number of retired instructions, the number of cache hits, and the number of cache misses every delta milliseconds. We specifically want this information as the number of retired instructions over the delta profiling window provides us with the rate of execution, while the number of cache hits and misses tells us how resource intensive the task was at the time. We repeatedly run this profile for every possible resource combination, each 100 times. All of this information is then aggregated together, which is illustrated in the table above, where each row depicts a different cache and memory bandwidth configuration, and each column represents a delta millisecond observation containing our data points. At this point, however, this collected information is still unusable because the differences between any two observations may or may not be significant. For example, for tasks like the Keneal benchmark, the rate of execution changes very gradually, and so while it may be clear that there are different phases when looking at the bigger picture, it isn't obvious at what specific point we should mark as the cutoff between any two phases. To solve this problem, we choose to use clustering, specifically expectation maximization clustering with a Gaussian mixture model. This technique is able to identify patterns in the raw data between the rate of execution and the number of cache requests and misses. After clustering, every data point is assigned an easily identifiable cluster label, and every unique label represents a phase. Because the data was clustered, observations that are assigned to the same label must share similar resource demands and rates of execution. Therefore, we can generate an average rate of execution using all the observations assigned to the same label to create a new rate which represents the phase as a whole. Depending on the application and its number of phases, we can often see long stretches of observations that all fall within the same phase, and so to reduce the amount of data we need to provide to DNA and DADNA, we collapse all contiguous observations that share the same label into one large one. For each resource allocation, we now have a sequence of phases with an average rate of execution. It is important to understand that a task could have the same resource needs and average rate of execution during two widely different points in its lifetime. And so we can see the same phase show up under various resource configurations at different times. The inverse is also true. Depending on the resource allocation, a task can have multiple phases at the same point in its lifetime, as demonstrated by taking a vertical slice from any point in figure C. Now that we have a formal definition for a phase and we know how to find and track them, the next challenge is how to utilize the phase information to better allocate resources at runtime. To start, DNA works by providing resources to tasks whose rate of execution would benefit the most from receiving additional resource partitions. Before looking at the details, we note that DNA is independent and can work with any scheduler. That is, it doesn't decide what tasks should run at any moment and instead takes this information as input. Additionally, DNA runs and computes new allocations in real time and thus needs to execute very quickly. If the algorithm were to run too slowly, then any execution speed benefit that a task receives would be wasted by the algorithm itself. At the high level, DNA works by assigning a minimum allocation of cache and memory bandwidth to each task currently scheduled and running on the system. Importantly, this initial assignment isn't applied to each task immediately, and instead, DNA waits until all resources are allocated before using memguard and cat. This way, we avoid unnecessary allocations that can be quite expensive. After assigning a minimum allocation, DNA then iteratively gives one additional resource to the task whose execution speed would increase the most based on the difference between its new phase, given the additional resource, and its current phase. To avoid excessive phase lookup times, we can pre-calculate this improvement factor given our profiling data to ensure that DNA remains fast. For full details on DNA and how this is done, please refer to the paper. By prioritizing tasks that benefit the most in terms of execution progress, DNA can effectively utilize resources while maximizing performance. However, since it doesn't consider task urgency, it may not provide enough resources in scenarios where tasks are particularly close to missing their deadlines. To account for this, we now introduce DADNA, DNA's deadline-aware extension. At a high level, DADNA is very similar to DNA, but as I mentioned, it additionally considers both its own deadline and the deadlines of tasks waiting to execute. To see why this is important, consider an example where a task is released on an overloaded system and begins execution much later than normal. In the figure below, we see that our task has release time R, deadline D, and start time S, and that because of its late start time, it is unable to make its deadline, even when DNA provides an efficient resource allocation. However, if the task had just received a few more resources earlier on, it would have been able to make its deadline. Note that DNA by itself wouldn't have normally made this decision because those extra few resources were used on a second task running on a different core which had a greater benefit. If task 2 had plenty of slack time, however, as shown in the new figure, then we can sacrifice this less efficient decision to improve overall schedulability. Let's look at another example where task 2 is now executing on the same core as task 1, and both tasks are released at the same start time. Task 1 is chosen to execute first, and in this example, DNA does provide enough resources for task 1 to finish by its deadline. However, now, task 2 will miss its deadline because of the same reasons we saw from the previous example. Therefore, we need DADNA to not only consider the deadlines of tasks that are currently executing, but for tasks that are waiting as well. So how does DADNA actually take this urgency into consideration? Briefly, DADNA first starts with the minimum number of resources just like DNA. It then estimates if all tasks will finish by their deadlines. If not, then DNA will assign a resource to the task farthest from finishing. If all tasks are estimated to finish, the remaining resources are allocated using the DNA algorithm. To account for the deadlines of waiting tasks, we use the notion of a virtual deadline. At a high level, virtual deadlines can quickly be calculated recursively by working from the task deepest in the wait queue and going backwards to the task that is currently executing. The end result is a virtual deadline that the running task must hit to ensure everything in the wait queue can also meet their deadlines. Once again, full details on both DADNA and how to compute virtual deadlines can be found in the paper. We will now evaluate how DNA and DADNA compare to a static approach on a real-world system. Our evaluation uses a prototype we built on top of the Zen 4.8 hypervisor. We used an existing memguard patch and extended it to work with Intel's CAT for cache control. We then added soft real-time support to Zen's real-time distributed scheduler and added the necessary phase profiling functionality to collect the phase data. For our experimental setup, we chose to compare against VC²M, a state-of-the-art static cache and memory bandwidth resource allocation technique which was presented in DAC of 2019. We ran our experiments on an Intel Xeon E5, which had support for Intel's cache allocation technology, and for our workload, we used benchmarks from both the Parsec and Splash2x suites, generating 15 unique task sets per utilization step for 225 task sets in total. Before looking at the results, we first show the runtime overheads of DNA and DADNA. On average, the algorithms take around 16 microseconds to allocate all resource partitions. Across all three percentiles, DADNA has the slightly higher runtime due to computing virtual deadlines and estimating if each task will be able to finish given its current resource allocation. If DNA or DADNA were invoked once every 1 millisecond, this would amount to only an additional 1.6% of overhead. Importantly, this demonstrates that we aren't limiting the benefits of our dynamic allocation approach due to excessive runtime costs. The first graph that we will look at is for task set schedulability. We plot the fraction of task sets that were successfully scheduled over its utilization. The blue and green lines show DNA and DADNA, while the red line shows the schedulability for VC²M. Overall, we substantially improved schedulability compared to the state-of-the-art static method. Specifically, at 2.6 utilization, DNA and DADNA are able to maintain 100% schedulability, while VC²M can only schedule 10% of the task sets. Our next graph shows individual job schedulability by plotting the job miss ratio over the same utilization range. Just like before, we can see that DNA and DADNA are able to significantly outperform VC²M. At the same 2.6 utilization, DNA and DADNA successfully schedule every job while VC²M misses 40% of its deadlines. These two graphs highlight that DNA and DADNA are able to accommodate substantially larger loads, due in part to providing far more efficient resource utilization compared to a static algorithm. Our second set of graphs measure latencies and use the same task sets as from our schedulability results. Each graph above shows a CDF for each job's latency over its deadline. The vertical line shown in each graph represents the point at which a job's latency is equal to its deadline. Thus, any portion of the data before this represents the percentage of the jobs, shown on the y-axis, that finished before their deadline, while any portion after this point represents the percentage of the jobs that miss their deadlines. The farther left the data trends means overall lower job latencies. As we can see, DNA and DADNA, shown by the blue and green lines, substantially outperforms VC squared M across a variety of utilizations, ranging from low to high load. Importantly, this demonstrates that our dynamic approach can yield substantial benefits even when the system isn't in an overloaded state. Our last graph looks at job latency when considering all utilizations combined together. Here, latency is shown on the y-axis in seconds, and the overall result for VC squared M, DNA, and DADNA are shown for average 99.99 and worst case job latency using the same colors as before. The results show that across all three percentiles, DNA and DADNA managed to provide at least half the latency of VC squared M's static approach. Furthermore, we can see that DADNA provides a slight improvement over DNA by considering the deadlines for tasks that are both currently executing and queued, waiting to be scheduled. In summary, isolation is incredibly important to achieve predictable execution times on multi-core platforms. Previous state-of-the-art techniques use static resource allocation to isolate core interference, but end up doing so ineffectively. By acknowledging that the resource demands of a task change over time, we are able to identify and define unique phases of execution which provide insight into a task's changing resource sensitivity and rate of execution. Leveraging this, DNA and DADNA are able to dynamically adjust cache and memory bandwidth on the fly at a low overhead cost. Doing so ensures that tasks have resources when they need them the most, which leads to higher utilization, fewer deadline misses, and lower latencies. Thank you very much for listening to our presentation.